I will start. It's a great pleasure to have Professor Ichiro Takaruchi. Takeuchi Sensei is a professor at Nagoya Institute of Technology and a team leader of the team leader of the data-driven biomedical science team at RIKEN AIP. He received his bachelor's, master's, and doctoral degrees from Nagoya University in Japan in 1996, 8, and 2000, respectively. He worked as a postdoctoral researcher in Montreal with Professor Yoshio Bengio. He got tenured assistant professor position at Mie University in Japan in 2001, associate and full professor at Nagoya in 2008 and 2015. His research interests include theory and algorithms for machine learning and its application to biomedical and material sciences. It's a great pleasure to have you again, Ichiro Sensei. So please go ahead.
Thank you very much for introduction. So I'm Ichiro Takeuchi, and thank you very much for joining my talk today. First of all, I'd like to thank the organizer for this nice event. Today, I'm going to talk about the selective inference for deep learning model-driven hypothesis. This is a joint work with my 3 students. So this is a very brief introduction of myself. So as introduced, I'm a professor at Nagoya Institute of Technology, teaching statistics, data science, and machine learning. And I'm also team leader of data-driven biomedical science team at RIKEN AIP. And the mission of my team is to develop AI and machine learning methods for data-driven science. So let me start from what I mean by data-driven science. So this is a basic flow of traditional scientific research. In traditional scientific research, experts build hypotheses based on their knowledge or experiences. And in order to verify the hypothesis, they design experiments and conduct experiments. Then use the experimental data in order to quantify the reliability of the hypothesis. This process would be repeated many times for scientific finding. On the other hand, in data-driven scientific research, the flow would be slightly different. First of all, big data on the research target would be collected. Then AI or machine learning algorithm would be applied to the big data, and hypothesis would be constructed. Then the reliability of the hypothesis would be evaluated again by using the research big data. Experiment would be conducted perhaps by AI robot, and this process would be repeated. Today, I'm going to talk about this part. We're gonna discuss how to evaluate the reliability of the hypothesis obtained by AI or machine learning. When we use AI or machine learning in practice, our task is not only to develop methods that have good prediction accuracy, but also to think about, for example, ethical, legal, and social issue in AI. Also, interpretability and reliability are very important research topic in these days. And today, I'm going to talk about one of the reliability, statistical significance of the results obtained by AI or machine learning. Reliability in AI is studied in various aspects. For example, robustness is a very important concept because the complexity of AI increases the risk that a small change in the data leads to a big change in the result. And this is a very famous example. This is a picture of panda. If we add a very small noise to this picture, then the AI recognizes this picture with noise as given. Even our human being can easily understand that this is still the picture of panda. And in this talk, I'm going to talk about the statistical significance. It is important to consider the statistical significance about the result of AI. because the flexibility of AI increases the risk of finding false positive result, like which seems to be meaningful, but it's just an artifact. For example, let's see a medical image segmentation problem. Here we have an original image, but this image does not have any tumor lesion, any object. But if we apply a segmentation algorithm to this image, then the algorithm says that this is the object region and this is a background region. If you carefully look at this object region, slightly different, but actually this is just an artifact. So if we think about quantify the statistical significance of this segmentation result, what can we do? So for example, we can think about two sample tests to see the difference between object region and the background region. And if we actually do these two sample tests, the t-test, then the p-value was 0.000, indicate that this is statistically highly significant. But you would see that this is something strange because the segmentation algorithm itself is trying to find object region and background region so that they are different. So therefore, we need to do something else. So this is the problem we are going to, I'm going to talk about today. For evaluating statistical reliability of the knowledge obtained by AI, uncertainty quantification of the knowledge would be required. In data-driven AI, data is fed into AI algorithm and the knowledge would be obtained. So if we quantify the uncertainty in data by a probability distribution, then we would also like to quantify the uncertainty of the knowledge by a probability distribution. There are many approaches for uncertainty quantification. In frequentist approach, this problem could be interpreted as the problem of deriving the sampling distribution of the knowledge. And if the problem is very simple, we might be able to do the exact inference. That means that deriving the exact sampling distribution of the knowledge. Otherwise, if the problems are a little bit more complicated, we need to rely on randomized approach or asymptotic approach. In Bayesian approach, the problem could be interpreted as the problem of deriving posterior distribution. Again, if the problem is very simple, we would be able to obtain the exact posterior distribution, but in many cases, we need to rely on MCMC or some approximation methods such as variational inference. Uncertainty quantification approach for deep neural network, such as dropout, ensemble learning, Bayesian neural network, has been discussed. But they could be also considered as a kind of approximation of the sampling distribution or posterior distribution of the knowledge we are interested in. So in this talk, we consider frequentist statistical inference framework. And let me review the basic notion of frequent statistical inference here. From data generator, we're going to observe data, and the data is fed into AI, and the hypothesis would be obtained. In order to quantify the reliability of hypothesis, in frequentist statistics, we're going to think about the so-called parallel world. In another world, if we observe data 1, then another hypothesis A would be obtained. In data 2, if we observe data 2, then another hypothesis B would be obtained. Something like this. So here, let me compare knowledge-driven science and data-driven science. In knowledge-driven science, hypothesis about a research target would be built by an expert based on their knowledge or experience, which we called knowledge-driven hypothesis. In order to verify the knowledge-driven hypothesis, we're gonna do experiment, and experimental data is used for quantification of the reliability of the hypothesis. Here, traditional hypothesis testing would be used. On the other hand, in data-driven science, the flow would be different. First, big data on the research target would be collected. Then, AI or machine learning algorithm would be used to build hypotheses, which we call data-driven hypothesis. And the main topic I'm going to talk about today is the selective inference. This is the method for evaluating the data-driven reliability of the data-driven hypothesis. So this is the outline of my talk. In part 1, I'm going to talk about the hypothesis selection bias and multiple comparison. In part 2, I'm going to introduce a technique called the conditional selective inference. Then in part 3, I'm going to talk about our recent work on conditional selective inference for deep neural network. Okay, let me start from the part 1 about the hypothesis selection bias and multiple comparison. So as an example, let's think about the medical image segmentation. The goal of this problem is to identify the attention that object region in a medical image by segmentation. Given an original image, something like this, we'd like to identify the object and the background. So to simplify our understanding, let's think about the 5 times 5 image with 25 pixel values. So an image is represented as an n-dimensional random vector of pixel values x. Here, n it would be the 25. So the random image x would be obtained by adding noise vector epsilon to the true pixel value vector m. Here, we are going to assume that the epsilon is normally distributed. And the segmentation algorithm could be written as follows. Given a random image x, it returns the set of pixels in the object region and the set of pixels in the background. So this is the segmentation algorithm A. So we can interpret the segmentation result as a data-driven hypothesis. So the generator is m and epsilon, and we're going to observe image x. This is a data, and by applying a segmentation algorithm, AI, then we're going to obtain the object region and the background region. And our hypothesis is that this object is actually different, something special, which we need to pay attention. This is the hypothesis we obtained. So let's formulate this as a statistical hypothesis testing problem. So here, the null hypothesis is that mean pixel value in the object region is the same as the mean pixel value in the background region. And the alternative hypothesis is that they are different. Here, the appropriate test of statistic would be the difference of mean pixel values between object and the background region, which we're going to denote delta x. Here, note that the m here, the true pixel values, while x would be the observed random pixel values. And the statistical significance of the difference could be quantified by two-sided p-value, which is defined as the probability of having greater difference than that we observe. So this is the statistical hypothesis testing formulation of the image segmentation result. So let me compare knowledge-driven hypothesis and data-driven hypothesis in the context of this image segmentation problem. If we determine the object region and the background region before we look at the data, then they are knowledge-driven hypothesis. In this case, we can use a traditional z-test or t-test in order to quantify the difference between the object and the background region. On the other hand, if we apply the segmentation algorithm, that means that we're gonna look at the data in order to determine the object region and the background region. Then this segmentation result could be interpreted as a data-driven hypothesis. They are dependent on the data and the algorithm. So here, O and B are the object region and the background region. In the knowledge-driven case, they are non-random. But on the other hand, in data-driven hypothesis case, as I denote OX and BX, this is random, dependent on the data X. So the data-driven hypothesis could be interpreted as the result of multiple comparison with all possible 2 to the number of pixels segmentation result. We can think about all possible 2 to the number of pixel segmentation result. Each pixel could be object or background. And if we think about the result of the segmentation algorithm is the one whose difference is the greatest among all possible segmentation results, then this is a kind of champion data. So we would need to collect the selection bias. This is indispensable for this multiple comparison. Okay, next, let's look at another problem, feature selection in linear model. Actually, this problem is the original problem where people study conditional selective inference. Here, the goal is to select a subset of 10,000 genes that are useful for predicting drug effects. We have high dimensional data, something like this. Y would be the drug response, and X would be like a flat matrix where each column represents each genetic factor from 1 to 10,000. By using some feature selection algorithm, we want to select a subset of genetic factors that would be useful for predicting drug effects. And let's say in this case, genetic factor 257 are selected. Then think about a linear model with the selected features, and each coefficient would be estimated by least squared method, as shown here. And let me formulate this problem more. And the data is X and Y. And for simplicity, we're going to assume that X is non-random here, and Y is the random variable, the only random variable we consider here. And the probabilistic model would be that the Y, the drug effect, would be true drug effect. That would be some unknown function of X plus noise, where noise is normally distributed. And the feature selection algorithm A is a function given the drug effect Y, observed drug effect Y, then it's gonna select a set of selected feature MY. And in the case of the previous example, MY is 257. Here, note that the uppercase Y would be random variable, while lowercase y is the observation. So here, we are interested in the linear model with the selected features by least squared method. And this could be also considered as a data-driven hypothesis. The generator is μx plus epsilon, and the observed data is y, and the AI select a set of feature my, and we're going to obtain the knowledge about the coefficient as the coefficient of the selected features. And the statistical hypothesis testing problem is of this feature selection problem is formulated as follows. So as the inference target, we're going to think about the population least squared solution. Here, we're going to input the μx, which is unknown, to define the population least squared. And our null hypothesis is that the effect of the selected feature j is 0, while the alternative hypothesis is not. Here, the appropriate test of statistic would be least squared solution of the coefficient. And the statistical significance can be quantified by two-sided p-value, which is the probability of having greater coefficients than that we observe. So same as before. Again, let's think about the difference between knowledge-driven hypothesis and the data-driven hypothesis. If the set of features are selected without looking at the data, they can be considered as a knowledge-driven hypothesis, and we can just use the textbook result, z-test or t-test, in order to quantify the statistical significance of the estimated coefficient. On the other hand, if the feature selection algorithm is applied to the data, that means that the selected feature are determined by looking at the data, then they are data-driven hypotheses. So they are dependent on the data and the algorithm. So this is again considered as the result of multiple comparison with a huge number of hypotheses. We can think about all possible feature selection results as shown here. And we can interpret that the data-driven hypothesis we have is the one that has the smallest p-value among all of those. And here, since we are looking at the champion data, collection of the selection bias would be indispensable in this multiple comparison situation. So, of course, multiple comparison is a very traditionally studied in the context of statistics. But in the traditional multiple hypothesis testing, only a handful of tests are considered. For example, a very typical example in the textbook about multiple comparison is that, for example, when we compare condition A, B, C, we need to think about the difference between A and B, B and C, and A and C. So 3 hypotheses are considered simultaneously. So this is a traditional multiple hypothesis testing situation. And in the context of genetic data analysis, which started around 2000, large-scale multiple comparison with tens of thousands of hypotheses were considered. For example, if we have tens of thousands of genes, if we want to test each of those genes, then large-scale multiple, it is a large-scale multiple testing problem. But here we have more hypotheses. The number of all possible hypotheses that AI or machine learning can produce is much more than the existing method can handle. So we need to develop some methods. So I'm going to summarize the part 1 by introducing the 3 approaches for multiple comparison collection. The most fundamental approach is to control the family-wise error rate. That is to control the probability of finding a false positive to be less than alpha. Here, alpha is the significance level, such as 0.05. And another approach is to control the false discovery rate, the expected proportion of discoveries that are false to be less than alpha. And the main topic I'm going to talk about from part 2 is not new, but recently popularized approach called the conditional selective inference. Here, we'd like to control the probability of finding a false positive conditional on the hypothesis selection event to be less than alpha. So I'm going to talk about what I mean by conditional on the hypothesis selection event after part 2. So this is the summary of part 1. So knowledge obtained by AI or machine learning algorithm is considered as data-driven hypothesis. And the statistical reliability of data-driven hypothesis cannot be properly evaluated with traditional statistical inference because of the selection bias. And this problem can be interpreted as huge scale multiple comparison problem, where the one is selected from all possible hypotheses that AI or machine learning can produce. Okay, now in part 2, let me talk about what is conditional selective inference. So this is the one I showed before in order to explain the basic notion of frequent frequentist statistical inference. And the key idea of conditional selective inference is to consider only the cases, that means only the parallel words where the same hypothesis is selected. It looks something like this. Here, in our observed data, we obtain hypothesis B, and we only consider the case. We only consider the parallel words where hypothesis B would be obtained. So it looks something like this. So intuitively, by considering only the randomness where the same hypothesis is selected, then we don't really need to think about the hypothesis selection bias. This intuition is actually correct. Let's look at this in different way. Let's think about this is a data space. A point in this data space indicates a data set. In the case of image segmentation, a point in the data space is an image. And in the case of feature selection, a point in the data space is a training data set. When we apply this point to AI, then we obtain hypothesis B. And if we think about another point is applied to AI, then another hypothesis would be obtained. But in conditional inference, we are interested in the set of points in the data space where the same hypothesis B would be selected. And it means that we would be able to think about the subset of data space in which a point would generate same hypothesis B. So conditional selective inference means that we're gonna make an inference only in the subset of the database as shown here. So again, intuitively, by considering only the randomness in the subset of this data space, the hypothesis selection event, we don't have to consider. So this is the difference between the ordinary statistical significance and the conditional statistical significance. So the p-value was defined before as the probability of having a larger difference than that we observe. This was the p-value for the segmentation problem. And what is the conditional p-value counterpart of the conditional inference, which is called selective p-value? Selective p-value is defined as the conditional probability that the probability of observing difference is greater than that we observe, conditional on the fact that the same object and background regions are selected. Here, remember that uppercase X here indicates random variables, while lowercase x indicates our observed data. So we only consider that uppercase X, where the same object and background region would be selected by the segmentation algorithm. So here, the main challenge of conditional selective inference is to characterize this selection event and compute this conditional probability. This is what we need to do in conditional selective inference. So to understand conditional selective inference, let's think about a simple example in image segmentation problem. Let's think about the most simple segmentation algorithm based on the threshold theta. If the pixel value xi is greater than theta, then we're gonna think about that pixel is in object region. And if xi, the pixel value is smaller than theta, then it is considered as a background. So here, in this very simple segmentation algorithm, selection event could be written as shown here. If the pixel I is in the object region, then xi should be greater than or equal to theta. And if pixel I is in the background region, and the pixel value xi should be smaller than theta. So remember that this was the selective p-value we defined before, conditional probability. And the conditioning part could be written as shown here in the case of this simple segmentation algorithm. This is just a linear inequality, a set of linear inequality with respect to the data xi. Okay, next, let's think about the conditional selective p-value for feature selection problem. The ordinal p-value is the probability of having larger coefficient than that we observe, while the selective p-value is defined as a conditional probability of having larger coefficient than that we observe, conditional on the fact that the same set of features are selected. Here again, uppercase Y indicates a random variable, while the lowercase y indicates our observation. So again, let's think about a simple feature selection method. That is not as simple as a threshold-based segmentation, but let's think about it. So as a simple feature selection method, we're going to think about marginal screening. Just to select K features whose correlation between Y and Xj are large. And if we standardize all the variables, then the correlation could be represented by an inner product of X trans in the form of X transpose Y. So if we want to select K equal 3 features, we just compute the inner product for all the features and select the top 3, the green one. Green ones would be selected and the blue ones are not selected. The hypothesis selection event here is as shown here. We just have a linear inequality of inner product. The inner product for the selected features, green ones, is greater than or equal to the inner product for the unselected feature, blue ones. So this is again just a linear set of linear inequality with respect to the data Y. So the selective p-value defined as this one could be represented, and the conditioning part could be written as a set of linear inequality with respect to Y. So let's see these two examples again, both in the simple segmentation problem and simple feature selection problem. In both cases, the hypothesis selection event could be represented by a set of linear inequality with respect to the data X and data Y. So let's think about the data space again. And here is the data we have. And we're going to think about a set of data, a subset of data space where the same set of same hypothesis would be obtained. And in both cases, these selection events are now represented by a set of linear inequality, which means that the subset is something like this. This is polyhedron in the data space. Actually, conditional selective inference has been actively studied after the seminal work by Lee et al. In 2016. In their work, conditional selective inference for lasso feature selection was studied. And in their paper, they introduced so-called polyhedral lemma. And this is a very brief summary of polyhedral lemma. This tells that for what kind of a problem we can actually conduct the conditional selective inference. So the two conditions are as follows. First, if the selection event is represented by a polyhedron, as the previous example, that is, the conditional event is represented by a set of linear inequalities in the data space, and the test statistic is linear function of the data, then the exact selective p-values can be computed based on truncated normal distribution. This is what Lee et al. Showed in the seminal work in 2016. So in order to understand why truncated normal distribution comes, let's see the picture below. So actually, by further conditioning on the sufficient statistics of the nuisance component, we have the sampling distribution on a line. If this is the direction of the test statistics, we're going to think about a line here. And we have this truncation by this polytope. We have a line segment as shown in the red line. So since the original data is normally distributed, what we have is a truncated normal distribution as in the right part of the figure. So this would be the sampling distribution, selective sampling distribution of the hypothesis when the selection event is represented by a polyhedron that is a set of linear inequalities. Actually, in the case of lasso, this is the case. So consider lasso is an algorithm to select a set of features and their signs, where M is the set of selected features and S is the set of their signs. And the test of statistics is the least squared solution for the selected model. So therefore, it could be written as a linear function of the data in the form of eta transpose Y. And the selective p-value for the lasso was defined as follows. The conditioning part is that the set of selected features are same, and the set of the signs are same. And this is just for the sufficient statistic for the nuisance component. So you can ignore about this. So this selective p-value has a nice desired sampling property as a p-value, which means that under the null hypothesis, this selective p-value is uniformly distributed conditionally on the selection event. So this is the desired property of the p-value should possess. On the other hand, if we forget about the selection bias correction, the naive, which we call naive p-value, these are highly distorted. So therefore, we cannot control the false positive rate to be less than alpha if we use naive p-value distribution. So this is the summary of part 2. Conditional selective inference has been actively studied as a promising approach for hypothesis selection bias collection. By polyhedral lemma, if the selection event is represented by a polyhedron, the selective p-values can be actually computed. This is the exact p-value, so this is the exact inference. And the selection event depends on each algorithm. So it is challenging to apply conditional selective inference to complicated algorithms such as deep neural network. But I'm going to talk about this challenge in part 3. So this is about our recent work on conditional selective inference for deep neural network driven hypothesis. Okay, so let's think about again the image segmentation problem by a deep neural network. Perhaps UNet is one of the most commonly used CNN for image segmentation task. UNet looks something like this. This has a U shape, repeating the downsampling, then upsampling. So this is the process of segmentation. UNet is free conditional convolutional network and has this kind of U shape. It is important to note that the CNN itself is a complicated function, but they consist of several basic simple components, such as convolution operation, ReLU activation function, max pooling, upsampling, or thresholding. So combining those simple components, CNN realizes very complex mapping. So let's think about the conditional selective inference for CNN-based segmentation. So if we write CNN-based segmentation algorithm as this way, given an image X, then what we want is to obtain the object region and the background region. So in order to do the conditional selective inference, what we need to do is to compute the conditional probability as shown here. This is the conditional probability of observing larger difference between the object and the background than that we observe, under the condition that the same CNN outputs are selected. And this is again the nuisance component, which you don't really have to consider. And how we can characterize this conditioning of the same CNN outputs are selected. So can we characterize the complicated selection event of CNN? So this is obviously not a polyhedron. So we cannot directly use the polyhedral lemma. So actually, the selection event of CNN segmentation algorithm is complicated. And this is just a schematic illustration, but it looks like something like this. It's very complicated. So remember that by conditioning on the nuisance component, what we need to do is to think about a line here. And in order to, we need to identify this set of line segments where the same segmentation result will be obtained by CNN. Here, the same segmentation result means that same pixels are selected as object, and the same pixels are selected as object, as a background. So how we resolve this problem? Our idea is as follows. We consider solving a sequence of segmentation problem for parameterized data in the direction of the test of statistics. Remember that this is the data space. So we think about moving the data along this line, then applying segmentation algorithm multiple times. More specifically, first, we're gonna consider multiple final selection events with additional conditions. We consider not only the conditioning event that CNN output is same, but also we consider that other final events are same. So then run the segmentation algorithm for each of final selection event on the line. So it looks something like this. So we first look at this region and check whether the same segmentation result is obtained or not. And if it is yes, we're gonna put the red line. Next, think about this one. And if the CNN output is different, we're gonna put it blue. We're gonna repeat something like this. So this is what we actually did for this problem. And so we're gonna identify the truncation region at which the same result is obtained and combine the probability mass of multiply truncated normal distribution. So how we can do this? What kind of additional conditioning we should think about? So our key idea is by additionally conditioning on the final selection events regarding the basic components of CNN, the selection event is characterized as a union of polyhedra. So I told you that the CNN composed of various types of basic operations such as convolution, ReLU, max pooling, upsampling, thresholding, etc. So consider a situation that an image is input to a unit, CNN. So then for when we input this particular image, let's think about, for example, in one particular unit of the CNN, and in the activation function, a ReLU activation function, the data is located in the linear part of the ReLU activation function. And for this unit, the data is located in the flat part of the ReLU activation function. Or, for example, in this blue one, max pooling, the triangle one is greater than the circle one. Or in the thresholding, for this unit, the value was smaller than a threshold. So we're gonna think about conditioning all these cases for each unit, whether the data is located either in the flat part or the linear part of the ReLU, which one is selected as a max pooling or something like this. So we're gonna think about very finer selection events. But by conditioning on these kind of things, we can obtain this kind of finer selection event. And actually, what we want to obtain, the subset of the data space where the same CNN output would be obtained could be computed by using parametric programming approach, something like this. So here, if you are not familiar with parametric programming, this is something like a large algorithm or regularization path. The computational cost of doing this is almost same as a large algorithm or parametric programming. So by doing this, we would be able to compute the exact selective p-value for the result of convolutional neural network. So this is an example when we apply the method to brain tumor image segmentation. So the above two cases is the case where the true brain tumor exists. So these are the true brain tumor. And this is a segmentation result. So when we apply a naive test without considering the selection bias correction and the selective p-value as we propose, both produces p-value almost 0.000. This indicates that the both says that the segmentation results are statistically significant. And this is okay because we actually have a true brain tumor. So this is a true positive case. But let's look at the bottom two cases. This is negative cases. We don't actually have true brain tumor in this image. So it looks something exists here because of the normalization, but actually this is just a noisy image. I mean, there are no brain tumor. And when we apply selective p-value, the selective p-value was something like 0.67 or 0.45. So this is far greater than, let's say, 0.05. So this means that this segmentation result is not statistically significant. But if we forget about the selection bias correction, just comparing the object region and the background region, then the naive p-value was 0.000, indicates that this falsely say that this segmentation result is statistically significant. So by considering the conditional selective inference, we would be able to properly evaluate the statistical significance of the result obtained by CNN. Okay, so this is a summary. Knowledge obtained by AI is a data-driven hypothesis, which cannot be properly evaluated by traditional statistical inference. And the conditional selective inference is a promising approach for exact inference for data-driven hypothesis. So the main technical challenge of conditional selective inference is how to characterize the selection event. Actually, polyhedral lemma enables us to handle selection event represented as a polyhedron. But many practical problems are more complicated than this one. So our parametric programming approach can be used for more complicated selection events, such as DNN-driven hypothesis. And actually, we apply this parametric programming approach for other problems, such as change point detection, outlier detection, clustering, etc. Okay, so this is the end of my talk. Thank you so much for your, for attending my talk. Thank you so much.
Thank you, Ichiro-sensei. I believe what these results indicate that we do need this statistical significant test, because for a neural network, you can just feed in anything.
Okay.
And you can, on my hand, I was wondering, there are people that try to use things like conditional GANs to come up with, let's say, posterior estimates for the decisions that you make with neural network and try to characterize some sort of a probability. What you're doing seems much more basic and fundamental. Have you considered somehow comparing and contrasting these two wildly different approaches?
Yeah, thank you so much. I completely agree with you. So what I did is more like a fundamental, and I'm trying to do it in an exact sense. Mm-hmm. But yeah, you are right. So there are lots of approach. So like in the early part of my presentation, I showed that there are various types of uncertainty quantification, frequentist approach and Bayesian approach. And I think what you mentioned is one of those approaches, but I'm not really sure whether the sampling either in a Bayesian approach or frequentist approach, can we actually, for example, if we understand it in a frequentist approach, can we somehow guarantee that this is, in some sense, we are estimating the correct sampling distribution of?
No, not really, right? Yeah, one must be careful about this because there's a lot of works that try to use just GANs and conditional GANs to just argue about the posterior distributions. Because there, for example, I think that in the example you showed, if you were to give those fake images, GAN would again give probabilities and uncertainty estimates and so on and so forth.
That's right. Yeah, actually, so the mission of my team is to apply these methods to biology and medicine. And in the field of medicine, for example, if we want to develop a drug by using AI, this kind of strict control of the false positive rate would be required.
Yeah,
so we need to perhaps develop more fundamental method that guarantees. Yeah.
I 100% agreed. 100% agreed.
So may I ask a similar question? So I think the approach you introduced today is more like an analytic method. So you try to compute the p-value in an analytic way. Yeah. But suppose we consider standard two-sample testing, for example, then we can use permutation test to numerically compute for any problems, right?
Yeah. But
can we apply a similar kind of numerical technique to perform selective inference?
Thank you so much. I think that's a very good point. And as an example, I presented two examples. One is segmentation and another is a feature selection. Actually, segmentation is unsupervised and feature selection is supervised. In the case of supervised, we can actually use permutation, label permutation, or we can actually do that data splitting. In the part of the data, we're gonna select hypothesis, then test in the remaining data. This was possible. But my main interest is in unsupervised learning setting. What we observe is just one image when we think about the segmentation. So it's very difficult to generate a randomized distribution of that image itself. So if we want to quantify the reliability of one particular result in the unsupervised setting, perhaps developing a numerical approach itself would be challenging.
I see. Thank you very much.
Thank you so much for a good question.
Are there other questions? Okay. So in the question and answer box, you could see a question.
Okay, so let me read out the question from Toyoizumi-san. Would the fMRI example false positive cases be unsuccessful if you simply divide the data into a machine learning training data set and the p-value computing data set? Yeah, so thank you very much for a good question. So this is exactly what I answered to Sugiyama-san right now. What we are interested in is the statistical significance of one particular image we provided to the already trained unit. So we are interested in whether particular segmentation result we obtained for a particular image is significant or not. So we cannot divide the data. So I hope I answer your question.
Are there other questions for Ichiro Sensei? Okay, so this then concludes our session. Thank you very much for this very nice presentation.
Thank you so much.
And we will continue next week with another talk. So have a great evening in Japan and great day in Lausanne.
Thank you so much.